Welcome back, students. Today we will be studying about atmospheric refraction. Now we have already learned that refraction of light takes place when light rays obliquely pass from one medium to another medium of different optical densities. In the Earth's atmosphere, there is air all around. However, the temperature of air in whole atmosphere is not same. Some of the air layers of the atmosphere are comparatively colder, whereas other layers of the atmosphere are comparatively warmer. The cooler air layer of atmosphere has higher optical density and behaves as an optically denser medium. The hotter air layer of atmosphere has somewhat lower optical density and behaves as an optically rarer medium. Thus, effectively, our atmosphere consists of large number of air layers having different optical densities. When light rays pass through the atmosphere, they undergo refraction while entering from one air layer to another air layer of different optical densities, and this type of refraction is termed as the atmospheric refraction. Under normal circumstances, the air just near the Earth's surface is optically denser. As we go up away from the Earth's surface, the optical density of air goes on decreasing and upper layers of atmosphere progressively become less denser. However, the physical conditions of the air layers are not stationary and may fluctuate depending on local conditions. We can understand atmospheric refraction through a simple observation. When we observe objects through a turbulent stream of hot air rising above a fire or a heat radiator, the objects appear to be flickering. The air just above the fire becomes hotter than the air farther up. The hotter air just above the fire is lighter than the cooler air above it. Thus, the hotter air just above the fire has a refractive index which is slightly less than that of the cooler air farther up. Since the air is not stationary, the apparent position of an object as seen through the hot air fluctuates and causes flickering of the object. This wavering is an example of atmospheric refraction in the local environment. On your screen right now you can see some common observations happening primarily due to atmospheric refraction. Let us discuss a couple of these. Let's begin our discussion with the topic of twinkling of stars. Now, when we look at a star on a clear night, the intensity of light coming from it appears to be continuously fluctuating. At one moment, the star appears to be quite bright, but at the very next moment, the star becomes dim, and so on. This random fluctuation in the observed brightness of a star is called twinkling of a star. The twinkling of a star is on account of atmospheric refraction of light. Now, when light coming from a star enters the Earth's atmosphere, it undergoes atmospheric refraction on account of varying optical density of air at different heights. The continuously changing atmosphere refracts the light from a star by different amounts at different moments. When the atmosphere refracts more light coming from a star to an observer, he feels star to be bright. However, when the atmosphere refracts less light to an observer, he feels the star to be dim. So, the starlight reaching an observer's eyes changes randomly due to atmospheric refraction and the star appears to be twinkling. Now, very importantly, stars twinkle but planets do not twinkle. The star is situated very distant from the Earth and behaves approximately as a point-sized source of light. As the path of light rays coming from the star, behaving as a point source, goes on varying slightly due to atmospheric refraction, the amount of light entering the eye flickers and the star twinkles. The planets are much closer to the Earth and thus seen as extended sources. So, a planet may be considered as a collection of a large number of point-sized sources of light. Although amount of light coming from each point side source flickers on account of atmospheric refraction, yet the total amount of light entering our eye from all the individual point side sources of the extended source will practically remain unchanged. Therefore, the planets do not twinkle. The apparent position of a star appears slightly higher than its actual position. We know that refractive index of atmospheric air is maximum just near the surface of the earth and gradually decreases as one goes above and above the earth. When starlight enters the earth's atmosphere, the light rays are traveling from optically rarer to optically denser layers. As a result, on account of atmospheric refraction, the light rays bend more and more towards the normal as they approach an observer on the earth. As a result of this bending of light towards normal, a star appears slightly higher than its actual position. So this is the apparent star position, which is slightly higher than the actual star position. Advanced sunrise and delayed sunset. The sun is visible to us about 2 minutes before actual sunrise and about 2 minutes after the actual sunset because of atmospheric refraction. By actual sunrise, we mean the actual crossing of the horizon by the sun. Now you can refer to the figure when the sun is near the horizon. The refractive index of air with respect to vacuum is 1.0003. Due to this, the apparent shift in the direction of the sun as seen by an observer to the earth is about half a degree, and the corresponding time difference between actual sunrise and apparent sunrise is about 2 minutes. Same phenomenon takes place at the time of sunset. Therefore, the apparent duration of daytime from sunrise to sunset is about 4 minutes more than the true duration. So this is the actual position of sun near the horizon, but how it is seen by the observer? It is above. So that's why for us sunrise happens 2 minutes before and sunset happens 2 minutes after. So in total we have 4 minutes more duration for the day. Shape of the sun at sunrise and sunset. The sun, when situated near the horizon, appears to be oval shaped on account of atmospheric refraction. This is the situation at the time of sunrise and sunset. When the sun is just near the horizon, the light rays coming from the lower edge of the sun pass through a greater thickness of atmospheric air than light rays from the upper edge of the sun. Consequently, the light rays from lower edge are deviated more and the vertical diameter of the sun appears to be diminished in size. So, the sun appears to be flattened, that is of the oval shape. However, at noon, the sun is overhead and light rays pass normally through the Earth's atmosphere and go straight without any bending. So, the sun appears as circular at noon. So, this will be all for today. Thank you.